In the English language, the word dither means to act indecisively. It's a bit of an old-timey word. If you've heard it before, it's probably in the context of, like, 19th century British literature or something like that. Now, as fate would have it, acting indecisively is also what I've been doing for the most part when it comes to making a video on dithering, the computer graphics effect, for about 5 years now. This has been on my list of shader effects to cover since, like, a really long time ago. And I've been putting it off for so long that I just kind of forgot about it until somebody reminded me a few days ago. Anyway, even if you didn't know what this technique was called, you have probably seen this stippled, checkerboarded, alternating colors pattern here and there in computer graphics over the years. It's quite popular in pixel art. Pixel artists often like to use patterns like this to create the illusion of having a larger color palette than they actually do. The example that I'm showing here is a simple black and white gradient across a square like this. This entire square is, in this case, comprised of exactly 2 colors, and if I zoom in on the dither pattern, you can see that it's just alternating boxes of black and white, where the darker regions have more black boxes and the lighter regions have more white boxes. This entire gradient is composed of 2 colors, but when you zoom out like this, you can use a dither pattern to create the illusion of having more colors. If we use what I might call a more high-resolution dither pattern, we can see that this looks fairly convincingly like a gradient, but once again, if I zoom in, you can see that we still have... we're only actually using 2 colors, black and white, but the dither pattern is a little bit more fine-grained in how it, like, stitches those colors together. You can also see if I zoom in, we've got some, like, weird bits where the boxes have some edges cut off, but that's mostly an artifact of zooming in. That's not part of the technique itself. Anyway, so this is something that's actually pretty simple to do in a shader in GameMaker, and indeed in a shader pretty much anywhere. I'm going to start by looking at this. This black and white square is the original square that we applied that dither pattern to. This is true color. If you zoom in, you can see that we're not doing any silly approximations. This is just being drawn through this here object 1 with the, it's got the sprite set as its sprite index, and we're just doing a little draw self. And this is going to come through on the screen if I run the game exactly as it looks in the room editor. We're not doing any dithering here. What we are going to do is we are going to write a little bit of shader code to make this happen. So I always have to give the standard list of prerequisites whenever I make a shader video. You will want to know how shaders in GameMaker work. They are a little bit different from regular GameMaker code. We're not going to be doing anything insane. We're not going to be doing any weird math or 3D or anything like that, but you will want to know the basic anatomy of a shader. The fragment shader, sampling from textures, things like what colors are and vector 4s are and that kind of thing. So the first thing I'm going to do is I'm going to get rid of gl underscore frag color equals that entirely, and I'm just going to set the output color to a vector 4 of just pure white, so 1, 1, 1, 1. That's going to give us a white rectangle. That is not going to give us a white rectangle because 1, I should give that shader a name, and 2, I should actually use that shader. Shader set shd dither shader reset when we're done, and now we're going to get a white rectangle. So we're not actually looking at the color that we're sampling from this texture. That's fine. We'll come back to that later in the video. The second thing I'm going to do is I'm going to define a function, and it's going to return a float, and I'm going to call it dither 2x2. And this dither 2x2 function is going to take a vector 2 position as an input, and it's going to return a single number, and that single number that it returns is going to be something between 0 and 1. And I'll discuss what exactly we're going to use this number for in a minute, but first I'm going to, I think, decompose this position, this vec2 position, into 2 integers actually instead of floats, and we can say int x equals int mod function, so we're going to say position.x mod 2.0, because in GameMaker's version of GLSL, we can't just say % for modulo. We have to actually use that function there. So we're going to divide position x by 2. We're going to take the remainder, and we're just going to turn that into an integer from a floating point number. I can say int y equals int mod position.y, also by 2.0. I think we can also do this as an integral vector operation, but it doesn't really matter because we're not going to use it like an integer. So I should also say that position, this is going to be most likely a position on the screen. It's not going to be like a position in world space or a position in texture coordinate space or anything like that.
Hey.
Anyway, so once we've done those 2 in mod operations, I can say int index equals x plus y times 2. Do pay attention. This is 2.0 when we do the mod operation because that needs to be a float. But when we say int index equals x plus y times 2, we're just doing times 2, no 2.0, because this is an integer operation and not a floating point one. And now we can think about returning a different value based on what exactly this index value is here. So x and y will both range between 0 and 1. And index here, x plus y times 2, is going to range between 0 and 3. So we can say if index equals 0, we can return a number, and that number can be 0.25. If index equals 1, we can return a number. That number can be 0.75. If index equals 2, return 1.0. I'm going to say 1.00 just so that these numbers are all the same length because I find that satisfying. And then if index equals 3, return 0.50. You know what? For reasons to do with the shader compiler, it's not actually going to like this. It's going to want me to have, like, a final return there, isn't it? I have a feeling. I'll see if it crashes or not when I try to compile it later. Anyway, so next we're actually going to use this dither function. And to do that, I can say float, let's say dither value equals dither 2 by 2. We need an input position, and I'm not going to use v_v text coord for this, as you might expect. As I said, I do want this to be in screen coordinates, and very conveniently, the graphics API provides us something that's called GL frag coord, and that's going to be a vector. I think it's a vector 4, which is going to represent the position on screen of the fragment that you're currently drawing. I just want the x, y. I think z and w are going to be like 1 and 0 or 0 and 1 or something not very useful like that. Anyway, again, this is just going to be the position on screen of the fragment that we are currently drawing. So 0, 0 in the top left, it's going to be like, I don't know, 1280 by 720 in the bottom right, or 1080, or 1920, 1080 in the bottom right, or something like that. And that's going to go into this dither function that is going to give us a value between 0 and 1, like this. And if I want to actually do something with that, I can do something like, say, GL frag color is going to be a vector 4 of, let's say, dither value on red, green, and blue, and just 1 on the alpha, because we're going to draw this with full transparency, full opacity, like this. You did not like compiling that, and I have a feeling it's going to be exactly for the reasons that I said. So because we know index will always be between 0 and 3, we know intellectually that this should always return one of these numbers, but the shader compiler does not know that. So it's going to want all of the possible code paths in this function to return a value, which means that I should just return 0.5 as like a default value, or have like an else or something like that, just so that all possible code paths lead to an outcome. So this, we are going to see that we have what looks approximately like a 50% gray. You actually might, depending on your screen, notice a bit of a strobing effect. And that's because pretty much each and every one of the alternating pixels on the screen are black and white. If you put your face really close to your display, you might be able to see the checkerboard pattern. I would not recommend putting your face that close to the display. You will make yourself cross-eyed, and that might lead to a bit of a headache. What I can do is I can zoom in on editing, or I can open up the Windows screen magnifier, and we can see if we zoom in that we do indeed have a bit of a checkerboard pattern. And I stand slightly corrected. It's actually not entirely like black and white alternating squares. There are some squares in the middle that are a little bit lighter and darker than others. And I am actually going to put that away because I was getting a headache looking at that. All right. So if we want to get a bit of a closer look without going blind, I can instead divide gl_fragcolor.xy by something like 4.0. And that's going to make each one of these individual squares 4 pixels instead of 1 pixel. And if we look at that, you might be able to see what's going on a little bit better. All right, so that's a 2x2 dither pattern. You can do other dither patterns. 4x4 and 8x8 are the other ones that I had in the demo at the beginning of the video. 4x4 and 8x8 are all going to look similar to this, but we are going to have a longer list of things that we can return. So let me start with 4x4. I'm going to want to, instead of modding this all by 2, I'm going to want to mod this by 4. So x and y can both have a range between 0 and 3. And index is going to be x plus y multiplied by 4. So index can have a range of 0 to 15. So if there were a list of 4 possible values that the 2x2 dither could return, there's going to be a list of 16 possible values that the 4x4 can return. And I'm going to go and fill in a few more of these. And if you don't mind, I'm just going to go and extend this list. So I can say 4, 5, 6, 7, 8, 9. Just like this, 0 to 15, these numbers that they return are going to have to be updated, and instead of typing those all out, I am going to just copy these over from my test project. And those are going to look like... Okay, the shader code editor does really not like... Am I actually going to have to type these out by hand? Alright, this is what the full layout of values is going to look like for the 4x4 dither. These are sort of magic numbers. They're not really magic numbers. I'll talk about where they come from at the end of the video. But these are the numbers that we're going to want for a 4x4 dither. I suspect, as before, I'm going to need to have the final one of these return something not inside an if statement if I want it to compile. And I'm not using the 4x4 dither, am I? I'm still using the old one. So let's go and actually install that here. So that's going to give us a 4x4 dither pattern. And you can see just visually by looking at it that there's a little bit more like fine-grained detail in here. So there were 4 possible shades of gray that the first one gave us, and there are going to be 16 possible shades of gray that this one is going to give us, and they're going to be arranged in a slightly larger tiling pattern than the original one was, than the 2x2 was. And you can imagine we can take this a step further. I'm going to do 8x8, and we can say dither 8x8. We're going to have a kernel size as it was of 8 pixels, a square of 8 pixels on each side. So mod the position by 8 on x and y. Index is going to be x plus y times 8. This is going to have a value between 0 and 63. And that means that I'm going to have a lot of values to copy and paste. Hang on a minute. Alright, the reason that I can't just, like, copy and paste a block of code over from the test project is that I did have it formatted slightly differently in my test project, which made this a little bit more of a pain than it would have been if I had proper foresight. Anyway, so this is a monster. This is an if-else that's 63 items long. I'm actually going to zoom out on that a little bit so that you can see more of it at the same time. This is ugly, but it is going to work, at least as soon as I make the final code path return a value not inside an if statement. And now I can say dither 8x8, and if I run this, we're going to have yet another pattern. So that's the 8x8 dither. Alright, I suppose I should start using this for something now. So right now, we are not doing anything with what we sampled from the base texture. So if we want to have this dither pattern interact with what you sample from gm_base texture in some way, you could take the number between 0 and 1 that it returns, and you could compare that to some threshold. And that could be anything you want, but I think a lot of the times if you apply this effect to pixel art, it's going to be something like the brightness of a pixel, or at the very least the brightness of like a color channel in a pixel or something like that. And we can say if I'm going to need, let's say, vec for base color equals texture 2D of that. If base color.r is less than the dither value, we can do one thing. Else we can do another thing. And we can say if the base color.r is less than the dither value, we can say gl_frag color is going to be, let's say, a black pixel. So 0, 0, 0, 0, 1. Let me format that nicely. And if the base color's brightness and/or red value is greater than or equal to the dither value, we could say that's going to be a white pixel. So 1, 1, 1, 1 on the color channels. And if we do this, lo and behold, we have turned our smooth gradient into a gradient of individual pixels that uses exactly 2 colors, but still gives us the illusion of having a smooth gradient, sort of. So that's our 8x8 gradient. If you wanted a reduced resolution, you could use one of the 4x4 or 2x2 dither patterns, and that 4x4 would give us this, and 2x2 would give us this, and I think this is the one that I showed at the beginning, which was really simple. It really only looks like 4 bands of colors without any of the more interesting patterns. I personally like 4x4 and 8x8 better. So why does this work, I think, is a fairly reasonable question to ask right now, because this kind of looks like a magic trick, because it takes a bunch of arithmetic that's not especially complicated, and it doesn't especially look like anything that has to do with color, and it turns it into basically a simple math function that will allow you to take a smooth image and, like, pixel artize it, and it will allow you to turn, like, gradients into base colors that just happen to look like a gradient by doing that little stipple pattern. So let's think about this. So I'm going to go to 2x2 because it's simplest. This function is going to return in a regular alternating pattern a value of 1/4, 3/4, 4/4, or 2/4. And that pattern is going to repeat if I open up this image in the sprite editor and like enable the grid so that we can look at it. It's going to form a repeating pattern that goes something like 1, 3, 4, 2, 1, 3, 4, 2, and so on down the line. And for each of the pixels in the original image, it's going to compare the brightness of that pixel to the value in a particular cell or in a particular pixel or in a particular like band of the image. And it's going to say, okay, if the brightness of that pixel is less than this threshold value, 1/4, it's going to be black. If it's greater than that threshold value, it's going to be white. Moving over, if the neighboring pixel has a brightness that's less than 3/4, it's going to be black. If it has a value that's greater than 3/4, it's going to be white. And it's going to do that for every single block or every single pixel in the entire image. And you're going to have, on average, in the darker part of the image, the pixels over here are darker, so most of them will fall below the threshold. Most of them will fall below the brightness cutoff. Meanwhile, over down here, in the lighter part of the image, it's going to be the opposite. So most of these pixels are fairly bright. Very few of them will fall below the brightness cutoff that we defined here, and as a result, more of the pixels are going to be white. And in the middle, it's going to be a mix of about 50-50. The bigger dither patterns, so the 4x4 and the 8x8, are going to have larger, as I think we'll call them, kernels. So instead of just looking at like a block that's about this big for a repeating pattern, the 4x4 will look at a block of, you guessed it, 4x4 pixels. And the 8x8 will look at a block of, I think I'm drawing this to the right size, 8x8 pixels. And that just gives you more resolution. There are more steps in between 0 and 1 that we're looking at in the larger dither patterns than there are in the 4x4, in the 2x2. And that just happens to be what... Apparently I like drew a pixel and then saved without meaning to. Can I get rid of that? Alright, you saw nothing. So that's why this works. It's very interesting. It's also extremely simple when you get down to it. So let's see how this behaves on some other images, because there are other things that we might want to do with this. So instead of using the black and white gradient, I can drop in this orange and brown gradient, and we can run the game on this and see what this dither pattern looks like. And this is actually not all that great. First and foremost, because it's still black and white, it's not orange. We are now simply looking at specifically the brightness of the red channel in this image. We're not looking at like the total brightness or the hue or anything like that. Remember, because a black and white image, RGB are all the same values, I just kind of grabbed the red channel and ignored the other ones, which works in black and white, doesn't work in other color, doesn't work with other types of color. So instead of doing this on basically the brightness of the image, we can do this on each color channel individually. And I think I'm just going to rearrange this code a little bit. So let's say gl_frag color. I already said the first time around, I can just initialize that to like a vector 4 of 1. And we can say if base color.red is less than the dither value, we can say gl_frag color .red equals 0.0, else gl_frag color.red equals 1.0. And we can do the same thing for green and blue. So I'm just gonna copy this for green and copy this for blue. And we're going to leave the alpha alone because we don't really want any like weird transparent areas. And if I run it like this, you can see that we have a gradient from orange to brown. This is actually probably not the most interesting gradient I could have picked for this, because these colors are kind of similar. But let's try out some of the other patterns. So that one's 4x4. If I try out 2x2, we're going to get much more simple banding. So we've just kind of got 4 colors like this. Not that interesting. 8x8 should be a little more interesting. And we can use 8x8 and get something a little more like this. Alright, so that's definitely a smoother looking gradient. It's still composed of, I think, just 8 colors. It's either 1 or 0 on the red, green, and blue color channels. So 2 options raised to the power of 3 for 3 color channels is 8. Not bad. So I'm going to try this out with a slightly larger image, and we can see how we can pixel artize these. This is a picture of some lovely Gazania that I encountered in the Brooklyn Botanical Garden a couple of years ago. We're going to try out that. I'm just going to go and drop that onto Object 1 as its sprite index. I am going to get rid of the divided by 4, because that's going to look a little bit weird when it comes to a larger image. So if we run dither 8x8 on this photograph here, we can see that we do have something that looks fairly convincingly like pixel art. Not like obviously perfect, it's obviously a very large image still. But this image has been downscaled or quantized to just 8 colors, and it still looks like we have many more colors than we actually do, because of our use of a dither pattern. Sort of create the illusion of colors in the in-between. And that's going to be 8x8 if I run this on 4x4. It might be a little bit blockier. Yeah, definitely a little bit blockier. And if I run this on the 2x2 kernel, it's going to be blockier still. There's a certain aesthetic in here that, like, if you've ever had, like, if you're old enough to have had, like, a 16-bit color monitor or something like that, where, like, colors in a photograph would have been crushed to, like, the extremes like this. It kind of looks like this. Dithering like this was a fairly popular technique back in the day to make the use of, like, old displays with, like, limited color space. Limited color depth, I should say. Anyway. So there's a couple of things I've been putting off so far in this video. One of them is where exactly these numbers come from. So this is known as a Bayer matrix, if you want to go and read more about those. When I was reading about dithering in the context of computer graphics, I only really saw 2x2, 4x4, and 8x8 Bayer matrices like this. And as far as I know, there's no reason that you couldn't have like a 16x16 dither pattern. It's just not something that you really do. I suspect 8x8 is just enough most of the time, and after that it's diminishing returns. These are all numbers that are like 1/4, 2/4, 3/4, and 4/4, scattered more or less uniformly throughout the range of possible index values. The 4x4, so there are 16 possible index values in here, so these are all going to be like 1/16th, 2/16th, and so on. 8x8 is going to be like 1/64th, 2/64th, numbers like that. The other thing that I know that if I don't address this, I'm going to get comments about, and honestly, I probably already have because I left this to the end of the video, and there are people who don't believe in watching the whole video before commenting, is performance. So this is a lot of if-else in shaders. Well, it's a lot of if statements in shaders anyway, and that has a way of turning people off. If you've ever read anything about, like, optimizing shaders on the internet, you've probably heard people making the claim that, like, if you have an if-else like this in a shader, it's going to be inefficient. For various reasons, including but not limited to that, like, the GPU will actually execute all, like, every single divergence of an if-else for every single pixel, and then discard the results that it doesn't need. And that's, like, half true. It certainly can do that if you have, like, a really insane branching logic in your shader, but for simple stuff like this, on every device that I've ever run something like this on, it hasn't been a problem. And what I believe the shader compiler will actually do is it will see something like this, which is very, very simple logic, and the shader compiler will actually flatten this out into a structure which will allow you to avoid any actual instructions that will cause a branch. Hey. However, if you do want to just not have to look at all these if statements, it is possible to define the results in an array and then just look up a value in the array. So this could be cleaner, but GameMaker's version of GLSL is ancient history, so you can't make this like a constant float array or something nice like that, but we can say something like float Bayer is going to be an array of 4 floats. Bayer index 0 is going to be equal to 0.25. Bayer index 1 is going to be 0.75. Bayer index 2 is going to be 1.00. Bayer index 3 is going to be 0.50. And then instead of doing that whole if-else Christmas tree, we can just say return Bayer index. And that will produce the same result. It's a little bit more elegant. I wish that GameMaker's GLSL ES version was like newer than about 17 years old, meaning we can just define this as a const array instead of having to do this, but no matter. If we were to run this, it would come out looking exactly the same, and you could do the same logic for the 4x4 and 8x8 matrices also. You know what? Let me just do that. How quickly can I actually reformat this? So if I say float Bayer 16, theoretically, I could use my best friend ever, the rectangle select, to just do that whole thing at once and then return Bayer index. And guess that wasn't so bad. This one's going to be 64. If you hold Alt and click and drag the right mouse button, you will be able to do a rectangle select like this, and it is very frequently rather convenient if you ever want to refactor code like this. Alright, it's not like shorter or anything like that, and again, if GameMaker's version of GLSL was newer, that there would be slightly better ways of writing that, but anyway, you could also do similar things for the dither values and the red, green, and blues down here. You could also use a step function, because this is just going to be like one thing or the other based on this, which might be slightly more elegant. I'm not going to do that right now. Instead, we've got ourselves a lovely dither pattern on here. So that's pretty much all I'd like to talk about here. Dithering is magic. There's a couple things you can do with it. In games, probably the most common thing that you would do with it is like crush the colors used in an image like this for use in pixel art or for use elsewhere. There's a couple things that I have used the Bayer matrix for itself without directly like doing anything to colors like this. Other examples that come to mind are things like in my sprite palette tool, if you mouse over a specific color, it will highlight all other pixels in the image that are of that color, specifically not by changing the color itself, but by just overlaying the Bayer matrix on it, or at least part of it anyway. And also in my 3D terrain tool, faces on the terrain that are facing more or less upwards will also get a similar effect as a way to denote like what is flat ground. And in the world of 3D, there's a slightly different use for dither patterns like this, which is screen door transparency. So for those of you who have never worked with 3D, transparency in 3D is a huge pain in the neck. And one of the solutions for working around that is to use some sort of dither pattern like this to selectively discard a certain fraction of the pixels in an image to simulate transparency. So you can think like if you want to pretend something is 50% transparent, you can selectively discard 50% of the pixels in the 3D object. If you want to pretend something is like 25% opaque, you could selectively discard 75% of the pixels in the object. I'll probably talk about that next. Screen door transparency, it's kind of fun. But this video has been going on for long enough. So, my name is Michael, I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the description of this video. I like to post videos on weird stuff you can do in GameMaker, so if anything like this appeals to you, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. You should all go check out Wizarducks and the Lost Hat, which is one of the games that I like to work on when I'm not doing YouTube stuff. Link to the Steam page can be found down below. I hope you all enjoyed that, and I will see you all later. Special thanks to Zenjamin, Zach Robinson, Squarecrow, Spydeye Games, Pixelated Pope, Mantaray, GameMaker, GameMart Indie, Edward Holt, DJ Gibbles, Brenton, and Boketa for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.